All right, welcome to what I think will be the last installment for this series for now. I think I've got the engine, such as it is, the demo where I want it, and this is in a usable state to if someone wanted to start building a game off of it or something like that, to where we got some primary functionality. Before we get into the code and some of the demos of the samples of what's going on, I want to talk a little bit about what I'm using here. I'm using MADS assembler, is what this is, on the Eclipse platform under Woodson. So this is just what I've been using for development on the Atari. There apparently is another thing or another way or whatever within this environment to do a Apple specific one, but I just didn't. I looked it up, tried to look it up. I couldn't really figure it out how to set it up and everything. There wasn't very many clear instructions compared to what there is for the Atari. And since I was familiar with this, I decided to just kind of adapt it. But there is some adaptation necessary here. So there's a couple things in here that are specific to doing it this way that have to be known. Some things are going to be like, how it handles byte assignments, where you say, okay, put this hard code these bytes into memory here at this location and under this, whatever label, and things like how it pulls an address for this. So this assign or command or whatever you want to call it basically gives the address of this. It puts a word in memory, and then it also gives the address, which there's a couple ways to do that. Actually, I found out later, so it doesn't have to be done that way. But anyway, so we get the address of this table of this word, these 2 bytes. And a few things like that, conventions for the MADS assembler. The other big consideration doing it this way, and possibly even anyway, really, is that when you're going to be putting this into a disk image, I'm using cider press. Again, there may be a couple other ways, but again, this is just the way that I figured out to make it work. Within the MADS assembler, you do opt-H because MADS assembler is set up to put a header that is specific to Atari, and we don't want that. We want a clean, relatively clean, you'll see in a minute, nothing else added. We're going to basically forcibly add, there are 4 bytes that are a header for the Apple format, for an Apple file. The first 2 bytes, which in this case don't matter too much because I used to have this at 8,000. Really, it should be at 6,000, but it doesn't matter because at least with cider press will replace these 2 bytes. But the first 2 bytes are the address that it gets loaded into memory on the Apple computer. The next 2 bytes are the length, and I'm not quite sure. It's not really per byte. I'm not sure. I think it's by sectors, like how many sectors there are. But don't forget, on an Apple disk, the sectors are chained, so you don't get 256 bytes per sector. You get like 253 because there's like 3 bytes that tell it where to go to the next sector for the in the file at the end of that sector until it hits the end of the file. So really, for this length, you just want to make sure you have enough, and that's why, if you'll notice, I put some bytes at the end here. I put a series of bytes so that when I'm looking when I'm testing and making sure that I got the right length there, I load this all up into the emulator, and then I go look at the memory locations in the emulator, and I make sure these bytes are present. Quite often I found that it stops somewhere up here or something, and it's missing all this other stuff because I didn't increment or have enough value here to tell it the length. This does matter. Okay, so cider press will replace this address, as I'll show you in a second of how to do that. So this is really kind of a dummy. It's just a placeholder. You want these 4 bytes here as a placeholder so that your actual starting of the file starts at 6,000 or wherever your address is. And subsequently, you have to back it off 4 bytes for the origin. So all of this stuff compiles to the right locations. So by backing it off 4 bytes, it adds the 4 bytes in, and then everything starts on your location you want to start at. So wherever you want to put this stuff, that's how you do it. This length, however, does matter. This will carry over, if you will, or not get changed. I don't know why cider press only changes the address and not the length. It's supposed to, but it doesn't. So I don't know why. Maybe there's another switch for that I don't have. The way I'm doing that, though, and the way you kind of put that into cider press, this is also another little tip thing that I figured out. One obscure forum mentioned this. I think there'd be more information about this, but for the Apple stuff, there doesn't seem to be as much programming information like this. When you assemble this, you'll get tilepaint.asm as your result. So in order to tell CiderPress that this is a binary file, and B, where we want it to load at in memory, you have to put this text in right after the file name. It's a switch basically that tells CiderPress to add this information to the header of the 6 apparently tells it that it's a binary file, and then it's the address that in memory that it's going to start at, which gets added to the file, the first 2 bytes of the file. There might be another switch for length, but I couldn't find it, so I don't know, and I was like, this is good enough, I can make this work, so I didn't mess with it. So I just hard-coded in, and just would keep increasing as I made the program larger, this value for the length. But that's one consideration if you use this method. If you have a more proper way of creating this, you can obviously modify that. But I want to point that out because I'm using a little bit of an unusual environment here. That is probably not what most people who develop or write, retro code for the Apple II are using. This is just where I ended up at and what I was able to kind of make work because I'm so used to working in this environment and how my process is. All right, so we're going to get into some of the code here. The other thing I wanted to talk about before we get into too much of the code specifically for how the routines work is I did add some switches in here. And I should probably... Okay. So I added a switch, and this is controlled... You'll poke a memory location, 300, which is in decimal, 768, in BASIC. So there's basically a basic program, a very short basic program that just loads this. Loads the graphic tiles that you want to use, and it loads this program, and then it executes at the entry point. It does a call to jump to the machine language routine. And this is the entire... so far, engine that lets you move around and display things and do animations. Okay. This controls whether, in a very limited fashion, whether we're using Ultima 4 or Ultima 5. There are a couple of specific things. I didn't go whole hog here with animations and whatnot, but it basically, because the maps start at different places on the Britannia disk, and in the case of Ultima 5, the Underworld disk, because they're in different places, from one game to the next. I think Ultima 4 starts at track 0, and Ultima 5 starts at track 13. So basically the first 65K of the disc on Ultima 4 is the map, and on Ultima 5 it's the last 64K of the disc, basically. There might be some stuff off the end, but for the most part that's the way it works. So I had to have that. I wanted to be able to have the same. I didn't want to have to compile the program twice for 2 different versions. So I put a switch in. When you'll poke this location, which I made it you'll see in the basic program. I just made it line number 1. I made it a very simple variable called U4, and it's either 0 or 1. 0 is Ultima 4, and Ultima 5 is anything non-zero, really, because it'll just fall through. So it compares that with 0. If it is 0, it just skips around because everything is already, all the kind of presets in here, since I developed most of this with 4, all of the hard-coded presets for things are for 4. And it just changes stuff for 5 where needed. So if it falls through because it's non-zero, it changes the location of Lord British's castle in the map because it is in a different XY coordinate on the map, and so on and so forth. Also, the tiles are different for the main character. Ultima 5, remember, has 512 tiles. And I've broken that up into 2 sets, so that it can be managed easier, because generally the second set, the second 512, is mostly animation frames and a few other things. But the character is in that set. Your main character is in that set. It's not in the first 256 tiles. Don't know why. So, in order to do that, I just picked a tile in the first 256 that looked like it, nothing we're really going to use right now. I don't know which tile they actually used, because you'd have to do it some way. Or maybe they just painted it raw to the screen from the second set. I don't know. You could do that too, but I wanted to keep this all within the same ecosystem of, putting a value into the map for your character, and it just the draw engine draws it without having to do anything special to check. So what I did was I basically copied the data from that tile for Ultima 5 into a chunk of data here, and then we just move it into the tile set. Oops, sorry. Did the wrong thing here. And we just move it into the tile set at the beginning if it's Ultima 5. So we just do the basic, start X at the end, decrement X, branch loop until X goes past 0, and then we exit. Then we construct some stuff here. We get the map disk. I did put in where you can actually move around the map disks. As I mentioned, I was talking about the map disks here a second ago. But so now we have it. So because originally I had just like a dummy map that we could move around in a very basic way. Show you what some of that looks like real quick here. Now I have the disk acceleration turned off here so I could see, because I wanted to be able to see when it was loading sectors. So I could actually see the little indicator over here and get an idea of, but also I want to get an idea of performance. This is running at standard 1 megahertz speed, so everything you see here that we're doing should be what a stock Apple II should do for performance. And with the disk routines turned off, that should also represent that as well. So this is a basic program. All this does is load in the appropriate tile set depending on what you want. See, we take the U4, you change this to non-zero for U5, it pokes it in. We set the graphic screen, we check it, and if it's 0 or 1, I set it to 1, I didn't really make it non-zero, but anyway. It loads in either the Ultima 4 tiles or the Ultima 5 tiles, and then it does the call to launch it. So that's basically all this really does. So there's not a whole lot of code here. And then to see that, and you'll see over here, disk light 1, it loads this thing. Okay, so now we're in the map, and this is that actually read from the Britannia disk. And this is a bit of a challenge to do this the way I want it. I have a certain way this works. I'll explain in a little bit, but we can move around. If you notice when we go left here, not too far, see it loads the next chunk, and that's fairly quick. I mean, I've got some test tiles up here. So this is my kind of standard way of when I was originally back in the day testing or messing around with the disk to get a sector editor, and you fill it with 0 through, I usually fill the entire sector 0 to 255 so that I could see all the tiles and what the tile numbers were. But it also works effectively as a boundary check in some respects. So I know that that's the corner of the sector, that tile, this water tile. So if I go one more space up now, it should load the next couple of sectors in, or load the next portion of the map. So if we come down, we'll do this as in kind of I'll just keep hitting up so you can see the speed of how fast it'll get the stuff and move it around and get the map prepped. So that's pretty quick, really. And you got to realize what this is doing is, this is not entirely optimized for map movement. You could do this better. I did it in the most, again, my predilection is to find the most straightforward way that will get it working. And then, unless I have a real clever idea, which sometimes I do, and then try to kind of say, okay, well, how can we improve that from there? In this case, it is the most straightforward way. When you transition from one part of the map to the other that needs to get from disk, it just gets all 4 sectors. It calculates where you are, figures out what the starting sector would be, which is basically the upper left corner of the map buffer. And then it loads that one and the next sector. And then it goes one track down from the original track and sector. So it resets that, goes down one track, because each row, each 16 by 16, each 16 tiles row is on one track. So if this was 0, 0 of the map, if this was the very top of the map, the very first part of the map, the entire map would be 16, or not, the entire track would be 16 tiles high and all the way across the track. Each sector would be, because the map is 256 by 256. So it divides out really nicely on this system. So every track is 16 rows of map and 256 wide with the sectors. So we just get 4 what I call quadrants. And that is actually shown. I've got a little map to kind of give you an idea of how this looks. So we basically, quad 1, quad 2, quad 3, quad 4. This is just how I broke it up in my thing, in my memory, or my mind and everything, just to kind of sort it out visually. So we calculate where we are in quad 1, and there are some adjustments we'll get into a little bit in case you're at the boundary. Because if you're close to the, because remember, this is the biggest thing to remember about this kind of stuff. This is, again, it's not fully optimized the best it could be. But if you're at this boundary, this boundary is, you're actually here. So you're actually at, if this was 0, this was the top of the map entirely, your position would be 5 down, right? So when we go up 1, this is now the next, in this case we're not at 0, but this is the next sector up, or in the case if it was the edge of the map, you wouldn't be able to move past that. Because you've got this little window, this little space here between you and the boundary. So if we are now looking, if we calculate, but the calculation when it says, hey, what X and Y position are we on the map, and what track and sector quadrant, you know, what track and sector, because each one of these quadrants is a track and sector reference. Where are we on the disk? So it figures that out, but it does not, until you code it, figure out exactly how far you are from that border. Now the border to the right and the border down don't matter because there's more map. No matter where we start, there's always enough map to the right and below that it accounts for that border if you're really close to this border here. So that doesn't matter, but it does matter here and here. So we have to check those boundaries, and if that's the case, let's say we were in this quadrant and we were at this boundary, we would then have to subtract up, or if we're over here and at this boundary, we'd have to subtract 1 over this way to the sector to move it to make enough space so that that quadrant now goes here, and we're now at this boundary, but we have enough to go over the, or I should say it, yeah, this boundary, that we'd be over, because we're technically like right here. So we go back 1, read this as quadrant 1 instead, make the adjustments in the buffer of where your position is so that you're now here instead of here, because here wouldn't display right. You'd end up getting some garbage in memory that's beyond the boundaries of where we want to be. It's complicated, but if you've ever done this before, you know how this, once you get into it, you'll figure it out. If you haven't, and if you've ever done this before, you know what I'm talking about. But we have to make adjustments for the upper and left boundary for that reason. And that math you can figure out. There's ways to do that. There's better ways to do that. But in this case, I get this quadrant, and then I move this quadrant into the map buffer. Then I get this quadrant, and I move this, because you got to move 16 bytes at a time, because it's got to be constructed a certain way. Because this is 16 by 6, oops, I should say. This quadrant is, of course, 16 by 16, but every 16 bytes is a line, but your map buffer, this kind of represents the map buffer, is really 32 bytes. So you have to copy 16 bytes here, then the next 16, then the next 16 all the way down through this quadrant, and so on and so forth for all 4 quadrants. So what isn't done, what could be done better if you really want maximum performance, is when you move beyond a boundary and you're going to recalculate all this stuff, let's say you're here and you move left, or actually let's say you're here and you move left, you would actually, well actually wait, no, I take that back. You're here and you move left. I take that back. I'm not doing that right either. If you move left here, oh yeah, if you move left here, you would actually internally copy this quad to here and this quad to here, and then re-get just this quad and move it around from the disk. And so you're only really getting 2 sectors instead of 4. Right now, with this the way it's designed, it just gets the raw sectors. Once it calculates which sectors to get, it just gets them and moves them into the map buffer. And I didn't want to mess around with the other thing because it's just time, and you know, it's not really necessary for this, because again, we're not building a game engine here, although you can use this as a basis and make those modifications if you really want to do the performance. But really, when you get down to it, this is actually performing quite well even then, because when we get beyond the boundary here, 1, 2, 3, 4, that's not very much. It's not too bad. And you know, that goes a testament to, since this is emulating, of course, we're, you know, who knows the actual speed, but even on the real game, you could tell it did pretty good with that because of how fast and efficient the disks were for getting data. And there's a method where if you wanted to write your own disk routine, this is just using the standard IOCB from DOS. So this is not really doing it in kind of the way, you know, this is incurring the memory penalty of having the full version of DOS there, which is not really how you do it if you were developing this as a real game. So it's using the IOCB from DOS, which is a whole handler, you know, thing, to do that, setting up parameters and stuff, which is basically, and I won't go into it because you can look this up, but just get beneath Apple DOS and you can figure this out. Get map from disk. Where's my IOCB stuff? Maybe yeah, where's my IOCB stuff? Hold on. Oh, here we go. So the IOCB is basically saying, oh, using DOS to get a sector, and there's just these settings. You know, what's the slot number? What's the drive? What's the volume? What's the track number? Some of these are default settings, and some you have to set. So I just basically set a value of Y and iterate through the table, setting the settings that are needed based on, you know, what we're doing. The sector buffer, the address, you know, and so on and so forth. Which command is the read command, get the sector, the jump to get the sector, and all that stuff. So if you were to, this is just a performance suggestion if you want to mess with it. So if you want to make your own sector get routine, and you really want to make it fast, and I don't know all there is to know about this, but apparently there is enough time as the head is, if you say get sector X, right, and it spins the disk and starts getting that sector, if you read subsequent sectors on that track in sequence, there is enough time to read the sector data and process, because it's stored in a GCR encoded type way with tables and other stuff, right? If you were able to, if you're very smart and very clever and want to get into it, there's enough processing time, barely, to decode those GCR encoded bits off the disk as it's being read. You'd be manually reading the sectors and all that stuff and kind of moving the disk around and stuff. But if you were to delve into it, people have done this where it's possible there's enough time to do that decoding in real time as the bits are streaming in from the sector. So you can literally decode on the fly. So it's one pass. And you can put that right in your buffer wherever you want to go. So people have used this method, by the way, to load a graphics screen. But instead of loading, like, say, if you do it in DOS and you just say B-load into the graphics screen, you see that Venetian blinds effect. That is doing a load the sector, you know, do the IOCB, set all that up. It loads the sector. It does it into the buffer, which it then decodes. Meanwhile, the disk is spinning until it's finishing all of that to then get the next sector. And that's why you see it load in parts, because it's decoding that stuff and then it has to move it into the memory of the graphics buffer. It's still pretty fast for an 8-bit old computer. When you see it happen, it loads the entire graphics screen in a few seconds, but it's possible to do that in one pass. And people have done this for loading screens where they start reading that sector and they start putting the data into the memory immediately and decoding it on the fly, so that the disk never spins an extra revolution. It reads every bit of every sector in sequence all the way around that track, and then you change tracks and continue on from there. And they're able to load an entire graphics screen of your splash screen in like less than a second or something like that. And people were shocked when people figured out how to do this. You have to pretty much manually control the disk entirely, as far as where the stepper motor is and all the track and all that stuff. Anyway, that's just a tip if you really, really want to do it. But the probably better way in between that is, like I said, you would just move the quad buffers around internally in memory, whichever direction needs to be done, and then just load the two sectors that you need to. But again, if you're not using DOS, you're still going to have to do a little bit of manual setup to get the sectors and where to put them and everything. And I wasn't going to get into that. I was just going to use the DOS stuff because it's quicker and easier and it's fast enough for this purpose. Anyway, that's a little bit of a side thing. So, okay. So let's get back to some of the graphics aspects. So, okay. I was originally talking about what I'd added and enhanced to this. So I also added, let me get down here where we can see some stuff. So one thing I added was a switch, another switch in the thing where you press the V key, okay? So V will switch in real time between the two different methods I'm using to paint the screen, which we talked about before, which is this you're seeing now is the optimized for size routine that's only a couple hundred bytes or whatever. And it's 8 or 10 frames a second, give or take. I've enhanced it a little bit, and it's slightly faster, so it's probably like 10 frames a second or so, 9 or 10. And we've got... so this is a much more memory-efficient method, which still performs quite well and is significantly faster than the retail game. And then you hit V, the V key, and it switches between that and the longer but much more optimized method, faster method. This is the 15 frames per second method. So that's an option for messing around, so you can test to see what things are doing. But the difference is that I have now added a routine in here that only repaints the tiles on the screen. First of all, when you move, if the tile has changed from the previous screen, so for instance, if we're here, and we go up, so this tile has not changed. It's still the same tile value. So it would not get redrawn. Only the ones that change. So really, as we move up, for instance, this one would change and be repainted, right? And this row would be repainted, and the castles would move down. So those are, and your character probably would not, because your character stays the same, which is handy. So it can skip that. So it skips the tile. It only paints the ones that have changed. That's for movement. When you're idle like this, the animations are done, only the animation tiles. It does a check, and it says, is this tile part of an animation tile thing? And the check is very simple, and it does not cover all the animations, of course. It just covers water and these flags. So it really doesn't do much compared to an actual engine. So you'd have a bit more going on there for compares for your animations to check for all possible animations that could be on the screen. But it only paints the tiles that are moving. So if you notice how this is performing, it's pretty good, but you can see a little bit of a shifting. But if we move up and you start seeing there's less and less tiles to have to repaint, you can see now it's moving much faster. So now if we switch between this and the full fast method, you can see the fast method's still faster. And it will be because the skip function skips regardless before it hits the call to do the thing. So now you can see it moves. If you do the so this is the slower method. This is with just a few tiles, it animates quite well. And with the full speed method, it's really fast. Of course, because I'm only drawing a few tiles. So anyway, just want to make that clear of what we have enhanced. We'll go over the code here in a little bit of how that was done, but those are some of the enhancements in here for that. Let me just check one thing here. Double check my. Yeah, okay. Okay. Just want to double check something, make sure I didn't do something else. So those are the enhancements I did for performance. Originally I had it's a funny story. Originally I had screwed up the routine, so it only drew the top row. So when you got something like this, where there's only one or two tiles, and it's only processing this top row, not the entire screen, because even though it's only redrawing X number of tiles, it's still processing every tile in terms of it's going through the buffer, it's checking for animations, it's doing various checks, and it has to set up certain things before, certain memory locations and whatnot in prep for drawing that tile before it hits the check. We basically do this animation check right before we would normally call the draw routine. And I had to do it that way because otherwise, if we skipped around it, there'd be things that wouldn't be set when you do need it. So anyway, and things that wouldn't be updated that would for the next tile and everything. So I originally had it that way, and these tiles were animating so fast it was just almost solid blue color, or you were just seeing lines just straight through. There was no sense of what that tile was. It was so fast because it was only doing that top row. It was only processing a few tiles, and so now when I got it properly worked out, you can see even at one of the fastest speeds, it's pretty fast, but it was comical. It was just before it was just comical. It was easily 10 times faster than this. Just a blur, Anyway, okay, so I think we're going to do a quick show since it's more fun to see this stuff than talk about it to a degree. Let's I got to load it first. U4GR draw 1. There we go. And so now we're going to set U5. U4, sorry. And we're going to switch the disk. Let's see here, where is that? Oops. Gotta find it. Okay. Okay. So now for U5, U5 has a different method for doing certain things. The tiles are still animated this way for the water, but they're in slightly different locations. So technically on the U4 map, and we'll talk about this here in a second with doing range checks. So when I do the check, it's probably up here actually. When we do the animation check, let's see where we're at here. Okay, here we go. So when we do the animation check, the tiles are in slightly different locations. So in Ultima 4, it's the first 3 tiles. In Ultima 5, it's tiles, instead of tiles 0, 1, 2, 3, 0, 1, 2, it's 1, 2, 3. So in order to not have to check each one of those individually or do other weird things, I just lumped it all together in less than 5. So 0, 1, 2, 3, 4. And that covers both Ultima 4 and Ultima 5 tiles. And it basically says, okay, we can repaint. This is the repaint. This is while you're idle and it's repainting the screen to show the animated tiles moving. So what we do here is, oops, let me get this over here. We check if it's less than 5. If it is, then anything less than 5 is repainted. Should say animated, is repainted. Now on Ultima 4, tile 4, which would fall within that range, is the swamp. So in reality, it's not fully optimized that way because you're technically repainting the swamp tiles on Ultima 4 anytime they're on screen, regardless of, because they don't animate. But you could correct that. Again, I just was trying to get this kind of working in a very basic sense. I don't have the flags animating in this one because, again, these are in different places. And also, but I didn't really put a check in for that. So basically, this is still going to animate tile 10, 11, and 14 in this tile set. So there's some, I forget where it is, but when you move around, you can kind of see those jumping around, which is supposed to be these flags. But I didn't change them because, again, I'm not trying to make a full engine here. I just want to have something that we can kind of visually check out. And I want to have a little bit of animations for some stuff. So anyway, so that's what that does. That basically sets a flag. The flag is set, this flag will be set on each tile to 1. To, yes, repaint the tile. It assumes the default is repaint the tile. And then this or this for the movement, this is when you move, and it compares the buffers. This disqualifies that. It says, no, don't paint that tile. So it replaces that when it checks those things. But the default, that way if I missed anything in the code, or for some reason it doesn't get a check right, or I don't have a branch right, and hopefully it will stay in 1, and it will. So the worst case scenario is every tile would always repaint. Worst case scenario, and I think this is showing. Is that switched around? That should be animating if it was. No, I think it's just grass. Okay, anyway. And the other thing I didn't, again, if you were doing something like this, similar, either recreating Ultima 5, or if you were doing a situation where you wanted to have, I don't know why my guy has a base here, but anyway, something's different there. Or if you were to do something similar to how Ultima 5 works, you'll notice this little corner piece of the shoreline is not animating. And that's because the way they did the animations in this game, for this kind of stuff, they added a new kind of feature. Let me see if I can go over here and... I think I may have that off a bit on the map. That doesn't seem right. Yeah, we definitely got something wrong there. Anywho. Okay, so you can see how they made this kind of these kind of shapes, right? For rivers and stuff. Tributaries and everything. Well, these pieces here, there's if you remember from the previous video with the purple... There was like a purple, what I called a mask. So what they do is they basically get this tile and the water tile, and then the exclusive ore with a mask for the water tile, and then place that here. The exclusive ore, these two together, using the one thing as a mask. And that then puts the water, just the water portion, whatever is masked out, which would just, it's kind of a shape. So it'd be like this shape in here after it's been animated. So that's how they're doing that. I thought I had this working for Ultima 5 for movement, so sorry on that. I was sure I had to, because it's the same method. It's the exact same. Oh, maybe my boundary checks are wrong, because I'm thinking that it's Ultima 4. Anyway, I think if we move up here, this is my testing. And you can see, okay, so now you can see how fast that's going there. That's moving along pretty quick. If we do the full method, it gets absurd. So anyway, yeah, I think it's moving around okay. Anyway, and now you can see when there's more on screen, it slows down. All right, so they do this masking method for water and some other things, and you could use that method for other effects too, really. Just take time. We are animating, okay, so just like before in the previous videos, the water and what you can't see here in Ultima 5, the flags, are being animated every frame. So we're not, the one other optimization you could do, which I have not implemented, was to go through and say, okay, like for instance here, well, we actually do have something there, but let's say we're here, and there's no animated tiles on the screen. You could have a check in there to say, is this tile an animated tile? Which would basically be this check here. And you could, but you're checking not for repainting, but to see if you would basically scan through the buffer every move, and you would just set up the animation. Say, oh, we've got these 3 water tiles. Okay, animate the water. Now the water, question on the water, if you animate water at all, you have to animate all 3 tiles because they're synchronized. So they go together, they fit together like a puzzle piece. So you'd have mismatches if you just did one. So water is an all or nothing proposition. You have to animate all the water tiles or not at all. But anything else, let's say the flags, for instance, and you could say, oh, let's see, there's no flags on screen, so whatever those tiles are, you know, whatever value these tiles are, and so we wouldn't animate those. Although to my mind, you know, these flags are small enough, they're just literally like, it's like 6 or 10 cycles. It probably isn't going to matter very much that way. So that's the other thing I haven't implemented to check for performance. It wouldn't make a huge difference because the whole point of the animation, because if you think about it, the whole point of the enhancements is to make this animation faster, really as fast as possible, to make this look smoother, right? If there's nothing on screen to animate, it doesn't really matter how fast you're looking at the screen. It'll affect movement slightly, but not enough, because with movement there's a whole other bunch of stuff that has to happen. So the amount of cycles necessary to do these animations, at least for the basic stuff. So in my mind, the way I would view this is we always animate the water, because water is going to be the most common animated element you're going to see in the game, right? So every frame we always animate the water. That way it's just done. It's always ready to go. We can then, and maybe the flags on the thing, because they're very small, anything really tiny, because between movements, you know, the movement's pretty fast here. And actually that was the other thing I was very impressed with, is how quickly this now moves around. That's quite fast with all these screen redraw enhancements, because it's only redrawing the tiles it needs to, so now it can move pretty quick. See, it slows down slightly there and slightly here because there's more unique elements. Anyway, so those are considerations. Again, I'm trying to keep an eye. I tried to develop this with an eye toward how you could expand it or use it in the future, and some of these ideas I'm talking about is why, because it's like, how would you use this? How would somebody use this as a starting point to make a game engine, and what would you need to add, change, or your considerations for? What are some of the considerations? And so I'm going to be giving some of that information and advice as well. So for the since we already kind of covered the animation, repaint, screen redraw, for the movement, when you move and we've now changed position, I do have an option. It's not here, but there's an option to forcibly redraw the screen. So if you teleport, for instance, or you're just doing something that you want to make absolutely certain every tile is redrawn correctly, there is a thing that says forcibly redraw the entire screen, all the tiles. But if you're looking at, when we're trying to do these movement things, the normal movement from one tile to the next, we would say we go through and we get our position. We go through as each tile is being set up to be painted on the screen, on the refresh, every refresh. We grab the index. We check, we load from map X number 1, map 1X I should say, that position in the map for that tile. We check it with 2, because as we move, which we'll see here in a little bit, we copy map buffer number 1 upon movement to map buffer number 2. And this becomes the check against. And this is the one that it uses to display. Okay, so that routine down there just basically compares them and says, hey, we are we're the same tile, so we remember redraw flag is always set to yes, redraw. So we say, nope, don't redraw that one. I originally had this screwed up as well, and I had where it went to check for that, I had it in the wrong place. I had it too early in my tile paint routine, and that's why I only painted that one row and messed up, so I had to move it. But because I moved it down to here, I think. Yeah, just figure if we need to redraw this tile. There is all of this overhead above that is necessary to be done first. Again, you could probably rewrite this in a way that would get around some of this, but I didn't really have time to go through it to see if some of this stuff could be switched first and changed around and done differently in a different place. Some of this probably could be moved. Doesn't need to be done at that time. It's just how I developed it and expanded it over the course of the thing. I haven't really gone into this for full optimization. So some of this stuff could be moved around probably, but you definitely need to have, it has to be after this because this is the main loop to go through the entire buffer. So we have to have that, which then skips down to here on the branch, so it has to be after this. This has to be done because we have to get the next row position on screen, and we have to reset it if it reaches the end of the row. So we kind of have to do this too. So it has to do all this stuff before it checks that. So it's kind of catch-22. Sometimes you can't do things in you got to do them in a certain order and with certain things done first. But anywho, so this basically when it comes back, it just says, hey, do we have a, you can figure out the logic there. It just skips over the paint. Basically we do our compare, and then we come back. Let's see. We branch around it. If it does need to be repainted, so we compare with 0. 0 would be do not repaint because it's the same tile or for whatever reason, and this then branches around that to actually do the routine, the thing, and then we jump. We got to be careful here because this routine is predicated on the idea that the return, there's a return aspect that will return here after the loop is done, and this goes back to the top because we've done some jumping. So that we're using the trick where you do, like for the jump tables, where you set up some kind of you do a jump, you do a JSR to a routine, and then that routine jumps to the actual routine you want to do, so that when you return to where the JSR originally was. Let's see, yeah. Which is somewhere up here in my main loop. That's the loop, but because we need to get it back to here. Anyway, that's the way I came up with it. But it uses that kind of trick. Similarly, the jump tables work the same way for the long routine, the big routine. I think I covered this before, but so I'll just touch on it briefly. But when we get to the full, fully doing we spread everything out, hard coded essentially, hard coded addresses and all that stuff for speed, for the repainting the screen, repainting the tiles. We use a jump as well, jump tables to get here, to get to this, so that the return from here goes back to the right place. And that way we're able to use an actual jump table, because you can't really do you can do an indirect jump, but it's you got to use 0 page, and you need a bunch of locations, which you don't have. So, and there's no JSR like from a table format. So we trick it by creating a jump. We JSR to something that jumps here, and then this return goes back to the original JSR. So we effectively create a jump to subroutine table, essentially. I think I covered that before, but anyway. Okay, so some more stuff in here. We've got a number, like I said, we got a number of checks for Ultima 4 versus Ultima 5 type stuff in here. Most of this is fairly straightforward. With the move, we create a command processor type thing. So we hit a key, we detect if we hit a key, we jump down here, we check it, and then we route it where it needs to go depending on what key is hit. Got to be careful because we're using branches, and they get, when you start comparing a lot of stuff, you end up with, potentially you can only go 127 bytes each way. So you got to keep things within a certain range. So you prioritize certain things here that don't require a branch, or that can branch to a short branch jump. So that these things, which compares two different, you can use the up arrow key, or you can use the I key, and IJKM or the arrows to move around. And then we jump to, again, the processor, how we process, so that the return comes back to whatever called this. So we return here. And then we jump to continue our main loop. And this main loop just goes round and round looking for key presses and doing screen redraws. And this is where you'd put, well, really this is where you'd put your commands, but this is your core loop. And then now the math, I'm not going to go into the math on moving them around the map very much, except to point out that the first thing we do is we check to see if we are at certain boundaries, depending on which way we move. So the first check is the absolute. Now, in the game, the actual retail game, if you go off the edge of the actual map, which is always at C, you end up looping around to the other side. I know how to do that, but it's a lot more code, and I didn't want to mess with it. So right now, if you're running around the map on this version, when you hit the hard edge of the map, you just stop. You just can't move any further. So all edges are like that. So basically we say, are we at number 5 in the absolute? This is the absolute X and Y of the map. Then we just don't allow movement. Then we check if we've reached the border line, and that is going to be, I don't know if I have an example of that. Not really, hold on. It's hard to kind of visualize. The quad thing. So this is if you're in the space between here, and if this were the edge of the edge, well, in this case, the upper edge of the map buffer, let's say. So this is the upper corner or upper edge of the map buffer. So there's nothing above there. There's no map data above that. So if you move up, and this would now put you into that space, we check for that and we adjust it. I won't go into the math on that and everything. I kind of covered that previously about getting the quads. That's essentially what this all does. So this just handles movement in that regard. When you go to the right edge, the upper edge, whatever edge. So we've got a move, redraw. There's a couple of routines I've gotten here that are redirects that you come here instead of doing like individual things like this. But this is basically the redraw routine that calls everything, sets everything up. We want to do a movement. This is for movement. So we say, okay, set the type of thing to movement. We clear. This is something I haven't implemented yet. That was this is going to be the animation check that I mentioned earlier, where you would check to see if there's any tiles on screen that need to be animated at all during the refresh. Just to animate them. Basically, you would check that. You'd say, oh, we've got an animated tile. This is before you redraw anything. So you on your refresh, every refresh of the screen, you first would say, are there any tiles to animate? And if you find a tile, you go and you animate that tile once. And there's ways to do it, and I worked out. I was going to do a table to make it faster, so you could just set a byte in the table for that tile number. And then, because if subsequent, if you have 14 tiles that are all water, you don't want to animate the water 14 times. You just want to do it once. So it would then put a non-zero value in that tile in a table that at that tile index number, and then skip it the next time if it finds it again, once per frame, basically, once per refresh. So you only get one refresh, one animation update per refresh. But I haven't implemented that yet. Just haven't gotten to it, and I'm getting good enough performance right now. I don't think I need to really check it, but you could do that to optimize. But again, it kind of becomes it's useful, but you want to have something like that though, because you do need to make sure you animate the elements that are on screen. But I just haven't implemented it yet because again, I'm not really making a game engine. I just want to get the concept in there and the construction. So this is actually going to go clear. It's a table. It's a 256 byte table. It basically clears that, just zeroes it out. Then we go ahead and we construct our new map position from the main map buffer into map 1. Map 1 is where we draw the map from. We then process it and draw the screen. And then we copy map 1 to map 2 for future moves, for the next move, for the comparison. Then we set our screen type back to only screen update. So we've now done we've already redrawn the screen, blah, 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 and now we say, okay, only do animations now until we move again. I did combine these into one routine, which I may not be using as much as I think I did. I thought I'd use this more because, let's see. But there's other places that might call this where these are basically these routines just grouped together. I think I may have changed things in a way that this isn't as useful, but it was useful in the beginning because this was all I was doing. I had a dummy map buffer and it didn't really need, or when I got the disk routines working, but other things now change and I don't think that's needed. This was also meant to be a little bit more, I thought I was going to use this method to be checking the various places, but it turns out I have to do, like for the animations and stuff, but I have to do them somewhere else. You could do this animation check, I think was going to go here. So we would, right now this animation, okay, so right now it's just animating tiles. It's essentially hard-coded. It just picks certain tiles and animates them, period. This is where you could kind of put in a processor to say, to check or have it, or change this routine to do that or whatever, or put that check in. Some of it has to be done, well, we'll see. And then we go ahead and repaint the screen. So this might be kind of superfluous in the end, or it's okay, but it's just one extra call, so it's not really a big deal. But it does give you a complete animate any tiles that need to be animated and repaint the screen function. All right, so now let's see. We are at, I think I've covered this before in the previous video when I was comparing the routines. The biggest change is going to be, let me pull one up real quick here, because I did change a couple things around. So I think I already showed this, the shorter routine, which I had, when I thought about it, I thought of a way to make it slightly faster. So originally it was set up, I believe, like this. No, not that. Oh wait, no, I'm in the wrong thing. That's here. Or did I? No, maybe I'm in the wrong one. Hold on, let me back up a bit more. I think I've got the other code here. Because I was using the indirect Y method. Apologies for not being better prepared for this because, okay, here we go. Okay, yeah. And it might be in, I don't think it's over here. So, yeah, I took this out of the one I'm currently working on. So originally I had this set up where we set up all our stuff and get all our addresses. And we did this whole dance between using Y to index for the load and the store. Based on these we prep the addresses up for the, where they go, where they get this. So this is we know that we get the tile address from there this is the tile data, the actual tile byte. And then this was where to store it on screen. And I was bouncing back and forth and loading Y and saving Y and using Y for both. And then I realized, well, wait a minute, if we know this value, or we know the address, we really don't need to be using an indirect zero page, because really we could use basically comma X, where this is a dynamically modified when the game runs each time. We change it on the fly. We actually change this address. And then X can then become an index, and this is actually a couple cycles faster than this, believe it or not. So I thought, well, I could, even with the overhead of adding this in, if it saves, okay, put it this way, if it saves one cycle per tile on this command instruction, then it saves 32 cycles per tile, okay? And if we look at our math, it's not a great deal, but it's a little more efficient. So we do 32 times 121 tiles. That's not right. 32 times 121. It's 4,000 cycles. Now there's some overhead, a little bit of extra overhead for creating this address, but it's a few hundred cycles. So we save something like 2,000 or 3,000 cycles. Not maybe a tremendous amount. Might be a frame rate, one frame FPS worth maybe, but it is a little more elegant, a little more of a solution there. So I did that in, I don't know. And let's go down here. Do tile. Yes, draw. Actually, where's my do tile? Sorry, I gotta find where it was. Redraw. Okay, here we go. So we've created references. That's the fastest. Store a tile, address +1 and we are somewhere. Where's my redraw? It's funny when you work on this stuff, you start losing track of where things are at, especially with the modern tools being so useful, which is what I'm going to use right now. I've done so much stuff since then, I've forgotten where the things are at. Oop, that's not right. Okay, here we go. So we've got our, and we use the absolute Y as well instead of the 0-page Y. So that's another cycle save. So now we've saved 64 cycles. But we have overhead. We have a little bit of overhead to construct these addresses. Because what we're doing is we're now hard-coding these addresses on the fly for each tile each time. But it's still only 1, 2, 3, 4 addresses to basically load and save. So it's again, it's like maybe a couple hundred cycles, but we're saving thousands of cycles this way. Because it's, remember, it's 100, it's every tile. So we basically take we get our table or graphics row table location, which graphics row we're going to paint to, and we store that information in these store. So we take it +1, which gets the low byte. This is obviously stored high byte, low byte, and then the high byte. And we do the same thing for the tile address, which we calculate. We've got a table to calculate. Well, we have a table for. So we basically index into the table for that, which was where I was before. And so we use this. We basically get this very easily here by just getting it from the, and then this is the other method. So then we store that at down here, tile address 1 and 2. So that's why I use a table, even though it takes up a lot of memory. It takes 512 bytes for the table for the index of the tiles, but it saves multiplying times 32 every time you want a tile. So it saves a ton of time that way. So we basically just load X with the index, get the low byte, get the high byte from the table, and off you go. So it saves a bit of. I definitely tried this both ways. This originally, when I did it the other way with the Y indexing, it was 17 total cycles. Now it's 33. But again, we're saving thousands of cycles, so the extra 16 cycles per tile. So we got 16 tile. I mean, I'm not going to do full math on this, but 16 tile extra cycles per tile. That's not right. Is 1936, but we should have saved overall 7,000. And a little bit of, well, that's the whole thing. That's including storing them. And then you have to add a little bit more for doing this part, which is, again, probably another 3, 6, 9, 12, 15, 16, probably 18 or 19 cycles, maybe. Let's say 19. So, you know, it's not a ton. You can do it either way, really. It's easier to do the other way with the Y. Well, not really easier, because we had to use Y for both This basically allows you to separate out the because in this case, where we put it on screen is actually literally hard coded. Because what do we do it here? Tile. Oh, that's detailing. Yeah, we get the and we increment. Okay, yeah. So what we do here is we got one here, the byte here, and the byte here, and we increment that by 1 to get the other byte that it goes to. Again, this is kind of an either or. It's a little more elegant in some respects, but it's also a little more ungainly because the other method you have to sit there and you have to keep preserving Y and coming back, and maybe a combination of the two would work, something like that. I just had this idea, thought, hey, let's try that. It does save some cycles though, so it definitely is a savings. All right, so getting back to some of the aspects here. This is a dummy. We just stuck that in there. The reference is here just to be a placeholder to have, so that it sticks 2 bytes in there that we had changed. This is for the long method, the larger memory method of redrawing, which we set up here. We index into our jump table, and then we store that jump table X, and increment X, and we basically take the address from whatever one of these we're on, based on X. X is the row, the row that we are, the tile row, mind you. So you got to keep in mind when you're doing this stuff, you're dealing with a lot of different terms that refer to different things, but they're the same term. We have a tile index, and we have a tile value, right? We have a row which could represent the literal single line on the graphic screen that we're currently on. We have a tile row, which represents basically this entire row of tiles. So on and on and on. So you got to keep your terms straight when you're doing this, because if you get the wrong one, you'll obviously be putting things in the wrong place. So that's dealing with because that particular method, the long method, basically each one of these routines is set up to do the entire row. And then you offset with X to get which tile across that row you're doing. So, because each one is 2 bytes, 2 bytes, 2 bytes, 2 bytes, 2 bytes. So you just, and 1 byte for the screen, or for this border offset. So basically X is going to be like 1, 3, 5, 7, 9, etc., etc. across the row. And that's what this uses to then go across that row. Anyway, so that jump table is for which row routine to go to for whatever row you're currently on. But I've covered that kind of in the other thing anyway, so we didn't delve into that too much. Let's see, that's the movement, that's the screen redraw. All right, so we're in our screen redraw. We kind of covered some of this. And again, I'm not trying to detail every single thing in here, just trying to get some of the methods and ideas down. Eventually, and I'll say this at the end as well. Eventually, I do plan to provide this somewhere. I'll talk about that at the end a little bit more because I'm not sure, and I'm probably looking for suggestions on that. Because I don't really develop for the Apple II retro community, so I have no idea where people put their stuff with this stuff. And I'll probably have things set up in such a way so that in case one of the discs for that has the tiles gets taken down, there'll still be the code out there for someone can reconstruct them on their own and get back to where they need to be to use this stuff. Okay, so we get our tile. Oh, we've already covered some of this. Yeah, we get our tile. Okay, so we get our tile. This is, I think I've covered this already, just the general draw routine. Get our tile, figure out what kind of redraw we're doing, and we just covered setting up the various places for where it would be drawn, and the addresses involved for that. And then we do the slower. Okay, so we basically jump back to the main tile at this point. And I can't remember why I did it that way, to tell you the truth. Because I know we're branching around here a lot. Maybe we do need to return there. Okay, so this is a possibility. I may have had this, Continue processing tiles. This may need to actually be this return. Like I said, it did some trickery with jumping and returning, so I may have had these jumps in. I may actually want to jump to exit done. In which case, if that's the case, if you start moving around a lot, you'll end up running out of stack, because it'll eventually have all these addresses on the stack and screw things up. So this would have to be checked out if you get into this. This is very important. So I'll try to track through the code here later and see, and maybe put a comment in about it. But this is something that I may have had initially done a different way when I first was putting this together. And then this got expanded, and now I'm doing it a different way from there. But I originally had this, for some reason, I had the return here. I always put a return in and an exit usually whenever I create a routine, just so that there is one, in case things fall through, and I want to make sure there's always a return, because I did that before where I forgot a return and then something didn't work, and I'm like, hey, and, oh, I forgot the return. But this may be not valid anymore. I'll have to check that. Because I'm not quite sure, because it would only be valid if I jumped down here, and I'm quite sure I JSR'd to some of these places. So I'll have to track through the code here to see what happens. Get map from just move redraw. That's a JSR. Move redraw. Da-da-da-da. Proc screen redraw. Also JSRs to tile paint entry. Because it will certainly work in a sense, but it'll obviously screw up as it repaints enough stuff on the screen. So we tile paint entry, tile paint entry. Well, that's jumping around over here. Yeah, okay. Jumping within. Yeah, I think that may be. I'll test that out and see, but that may have to be. We just change this, take this one out, and change that to go here, if that's the case. So keep that in mind if you're doing this and seeing these videos and you plan on using this or trying to modify it. And I'll mess with it and see if I can trace that a little bit better and see if I can get a more solid answer. There's a problem with this stuff. It gets so big and so spaghetti that eventually you lose track of why you did something like that a certain way if you change things, And again, I think I originally had this done a different way with the whole jump. I think I had jumps more than JSRs or something for testing, And then I more formalized it into routines and stuff. All right, this sets up the jump table. We covered that. That's the checks for whether we animate or do the thing. This, I think I covered it in the other video, but this basically just gets the current tile row, and sets it as an index to use to get the address from the tile, or from the graphics screen row or line number that would go to, that the current one would go to. I think this is for the starting, bottom of tile. So this is for the starting point of that. And this is, then we store that. Okay. Okay, we covered some of this, the shorter method for drawing, and it's done in the other video too. That's okay. I think that's basically it. So it's a lot of code, but it's not really too much to figure. We got some. Oh, I should come up here. Okay. Wait. Oh. Okay. Go up to where we hit that section, and then we'll come down. Okay, here we go. All right. So the animation routines right now, I started to work on some of this, of what it would check and blah, 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 but this is just placeholders. For now, we just animate the water, animate the flags. That's this stuff here, just basic stuff, which is, the water moves down 2 bytes, and you take the bottom 2 bytes and put them on the top. Town flags are just swapping literally 2 bytes, so it's pretty easy. Animate castle. I was attempting, this does, okay, so one thing I did here, this is another thing that just, it doesn't work. I haven't found a way to do it. On most computers, to make a random number or a pseudo-random number, you can usually peek some ROM or some other location that changes frequently. Quite often something with the vertical blank or the screen refresh, because that's happening 60 times a second. If there's any kind of value associated with that, it's going to change and fluctuate a lot. And sometimes you don't need, well, sometimes you do need random numbers that are fairly random, but you want to make sure you get numbers that are not always, well, they could be sequential as long as you get them at a different time. So even a sequential number, if something's counting in sequential fashion, if it's doing it fast enough, it can work. So this is to kind of simulate that, and I couldn't really do it. I was I couldn't find anything like that in the Apple. I found a couple of spaces in memory that changed, but they didn't change fast enough. So I couldn't use them as any kind of random check. So there's some stuff in here that's for that. But what I did was, and this is just a garbage way of doing it, I just created a counter, incremented it, and then just animated the town flags at different intervals, just compare 3 on count 12, count 3, count 6, so that they were just not, and count 9, so that they were just not, the flags were not flipping back and forth in unison. So if you had, like we see Lord British's castle here, let me actually do the Ultima 4 one, since we're talking about it now, and you might not have even noticed. Let's do the, we could just run this. So this is set up to run Ultima 4. So what we're going to see here is, oh, wrong disk. Ha! That'll do it. Sorry. Let's see, disks. Okay. That will definitely do it. So pay close attention to the flags now. You'll notice they move at different times. They still, if you look at one of them, any one of them, they will move on an even interval, because obviously I'm doing a count, right? So every one of those counts that it increments is a frame. So every 12 frames they change. So if you look at just the town over here, you'll see blup, 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 and that's an even interval. But between the two of them, they're on different times. So sometimes they're kind of synchronized, and sometimes they're different. See that change, and that gives a it's a cheap, very cheap way of creating, not even pseudo randomness, but just making sure that something like this is not synchronized when they're both on screen at the same time. There aren't too many instances of this in the game because there's not usually towns that are that close together, but it makes it look a little bit nicer, and it was a simple thing to do. I tried to get it random and come up with some kind of random number that I could truly make, because I was going to keep this method, and then I was going to add a pseudo-random number in the middle of that would trigger at some other time, so maybe the flag would go, instead of going blip, blip, it would go blip, 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 or something like that, but I couldn't get, if anybody knows of a way to get just a rapidly, all I need is a rapidly changing number somewhere in the memory of, that I can peek, or can get, somewhere in the memory of the Apple II. I don't care what values it's giving. I don't care if they're sequential even. I just care that it changes faster than 12 times a second. So if anyone knows, please leave a comment on that, because I don't know the system well enough, and I couldn't really find any information. Everything I looked at having to do with random numbers was like a monster amount of code to simulate it, and I'm like, I don't want to do that for this. You may want to do that for your project, though. Okay, so then we got some clearing. We clear the animation check. We copy the map buffer from map 1 to map 2. These are some of the routines. Construct the map buffer. This, as I said, as I kind of alluded to, does the whole copy thing 16 bytes at a time from the map buffer into the map 1 and map 2 areas. You can work out the math on that if you need to. Map move from sector. Move the sector buffer data to one part. This is what handles copying the sector buffer, setting up for the sector buffer when to move to either quad 1, quad 2, quad 3, or quad 4, depending on which one we set. I think this calls that. So it basically does a loop and has your starting I hard-coded some of the starting addresses because the buffer is in a particular place, and the offset for that we know, so you could hard-code those in. Because when you think about it, let me see if I can find the quad. The quad here. Where's the quad? Nope, not there. Maybe it's down below. Okay. So when you look at your quads, these are this is the map. This is the map buffer that holds all the map data that you pull from disk. You know, this is byte 0, and this is byte 16 because it's 32 characters, 32 bytes wide. And then this one is, you know, 512. It's halfway through the buffer. And then this one is like 512 and 528 and 16. So we kind of know where those points are, so we can use those more directly. So we basically set that up, and that gives us the quad moves to move the quad, move the each data into each quad, into each quad from the sector buffer when you get the map from disk. This is very complicated. I'm not going to go into this too much. I already kind of covered it a little bit of how it determines which sector to get. But basically, the core thing to this is, because we have, and I did that wrong, because we have these quad setup things, what we're trying to determine, and this is the quick and dirty way of doing this, and seems simple enough to work with, is we take our absolute x and y coordinate on the map and divide by 16. That will always give you the quad that character is in. However, and again we talked about the offsets, they could be close to these borders if that's the case, right? And you really only care about this border and this border. And we talked about how to modify that. So, but that's how we basically derive the essential starting thing. So the way to look at this is that you could track your character, like when you move, let's say you're down here and you move right. You could just move these two sectors over, which is the proper way to do it, and load in the next two that would be the next two for the map. That's a lot more figuring, because you got to figure if you're in this quad or in this quad, because this is a track. This represents one track, and this represents the track below it on the disk. Because remember, each tile row, each is 16 characters tall, 16 tiles tall, represents a track. For this, the way this works, because I'm just reading all 4 sectors, is I only do the raw X and Y calculation, and that always puts you into this quad. In other words, we're always starting here. Whatever we calculate, whatever track and sector we calculate that you're where you are on the disk from your absolute map position is always going to go here, unless you have to adjust because you have to go up or over. But even then, it still goes here. So if that's the case, if you have to adjust it over, yes, you're always starting with this upper corner as your starting point for track and sector. So we figure out this track and sector. If we find out we're too close to the border, we subtract 1 from the sector. Sectors go this way. If we're too close to this border, we subtract 1 from track. Tracks go this way, right? And so we're always starting. Our starting point is always quad 1. Instead of trying to track moving quad 2 and 4 left and then loading in 2 new sectors over here and all the math involved with that, I just decided it was easier just to get all 4 sectors, because it's linear. You take this, you get that sector, track and sector. You add 1 to the sector, you get this one. You subtract 1 from the sector and add 1 to the track, you get this one. You add to the sector then, and you get that one. So it's very easy math and increment decrements to develop, to put this in place. And then as you load each quad in the sector, you move that quad into this space. You move that quad into this space, and so on and so forth. So it's very straightforward. I think performance-wise, it would do as a method. For the most part, it does not account for, as I mentioned before, wrapping around the map when you get off the absolute 0 or absolute corners of the map, of the full map. So you can work that math out on your own. I can do it. I've done it before. I've done it for a couple different engines like this, but it's just a royal pain in the neck. So I didn't want to take the time to do it for this, because this is just a demo and a proof of concept anyway. So then we check for, let's see, go for disk yet. Okay, yeah. So we also, and again, this is because of this particular thing, you wouldn't use this normally. But this checks to do the offsets for the sector, for the track rather, if it's U4 versus U5. U4 is already 0. U5 we add 13 hex because that's where the actual map starts. And then we got some other stuff here to check for. Oh, that's the jump. Then we get each of the quads, load it up, call the routine to move it. The get sector from disk, again, this is the IOCB, and that's basically it. And then we got just our variables for the map X, and you could put these anywhere. I just put them here because they're only used occasionally, so having them in 0 page to save a cycle is not really that important. because they're only checked a couple times in any given thing, so they're easy enough to work with. These two you might want to put in 0 page because they do get manipulated a bit more, but that's also going to be within the movement routine, and everyone knows there's going to be a gap of time in the movement, so a few extra cycles there is not going to hurt. And the quadrant and the table starts, redraw routines, and all these other flags and such. So that's basically the code. I'm not going to have this fully documented. You may have to do a little figuring out on some of this stuff. I'll try to document as much as I can to give the methods. That's why I'm making the videos too, to kind of give a little more of an explanation of what the methods are here. So if you're looking at the code and wanting to mess around with it, you got an idea of what it's supposed to do, and that'll maybe help you figure out the code. It's not terribly complicated. I'm not one of these super genius programmers. I'm just good at figuring things out and hacking things together, and sometimes coming up with a little bit better methods like I did. But for the most part, I'm pretty straightforward on my code and my stuff. The fanciest stuff I did in here is stuff like the self-modifying addresses and stuff like that. That's probably the fanciest thing I've done in here, and the whole getting around the fact that there's no JSR table jump and making a method for that, which is not my method. It's somebody else's. Mentioned it, but I just kind of adopted it. Did it a little bit differently than what you see the way that's done, but similar method. So that's about as clever as I get as far as that goes. But I think I came up with some good stuff here. I'd like to think that it is at least interesting. And if we're looking at, let's see, if we do the, that's Ultima-4. So anyway, yeah. So I'm sorry this all has been a bit of a rambling thing. I wasn't really planning necessarily on doing videos on this, so I didn't have like a bullet point prepared thing. I just kind of been going by the seat of my pants on this, trying to cover everything. That's why there's going to be some repetition, because I wanted to make sure I covered everything, and some things I may not have described the best way before, and hopefully got a little bit better this time. So from here, I don't know if I'll really mess with this too much more. I just wanted to get the basic stuff down like that, and satisfy my own kind of curiosity as to whether this would work and what it would do if it did, and what I could come up with. If anybody's got some improvements, by all means, I'd love to see more of this stuff, like work out in some way, or someone build a game engine off of it. But anyway, the thing I got to figure out next is how we get this to everybody. I got to find a place to put it. We could certainly probably do Atari Age at least, so we could try that. If there's any other place that's a better repository for Apple II retro programming stuff, that would be someone let me know. That'd be great. This, just doing a catalog here to show you. So I'm going to make this is the kind of the primary disk. It doesn't let you make the stuff. We'll try to put that out. The programs are here, but the data is not. But this has all the final tile sets. So this has U3, U4, U5, the two U5 tile sets, and the current programming for making this work. The actual, this I'll have to actually put somewhere, because again, this is not an Apple image, but the same thing, I'll just have to put it there. But either way, but what I'm probably going to do is I'm probably going to make a version of this disk that does not have the tile sets, just in case this one gets taken down. I really hope people don't care, because we're not trying to take anything away from the original game or whatever. We're just trying to make an engine that works like Ultima, and the tile sets are just there, and they're easier to use instead of me trying to spend days designing tiles to use as a dummy. So I just use the tiles for that purpose, not because I have any interest in distributing them or what have you. It's just there for testing, for testing this concept and these routines. But just in case something like that were to happen, I'll make make a version of this disk that doesn't have these on there. So you'll still have all of the code, and then I'll make there'll be 2 disks, well, really 4, but maybe 3. There'll be this disk like it is. There'll be the disk without these tiles, and then there'll be the other disk, which is going to be I think this one, which has these graphic files that these make files are these tile make programs make, as I described in the other video, make from these .gr. These .gr files are the kind of source graphic images that you load this in the graphics memory. So I'll probably put this one out as well, and maybe I'll take the actual final sets off of here, off of this one, because they'll be on the other one. But anyway, I'll work that out. But I'll have a couple versions. So just be aware there'll be a couple versions of this, and refer to the videos for what each one does. There may be some duplicates, like this tile make is going to be on the other disk and stuff like that, because I just used this disk to make that disk as I kept working, and I just deleted off the files. So there'll be some duplication there. They should be the same programs, though. And then on the other disk, there'll be the newer programs to run all this stuff. So that's about it. Hope it seems like some people have liked what I'm doing here, so that's nice and good to see. And hopefully you, if anybody wants to mess around with this stuff, it helps to. This will help to make sense out of it, and you can use it to maybe use some of the techniques or some of the code. You can freely use the code. I don't care about that. I'm not interested in keeping any kind of ownership on this stuff, because it's just, again, this is just proof of concept stuff. So feel free to use it all you want, and modify it if you want to, and make your own stuff out of it, or use any of the concepts in here, the tables. At least another way to look at this also is that at least there is, you got some tables that are useful here. If you're making any kind of a tile engine, you've got a table here that does at least every 32 bytes. You can make different size tiles, but if you're making 2 by 16 tiles, well, now you've got a table that gives you all the offsets into that for that, so you can just immediately go in there. You've got the graphics table, which this is the part that surprised me the most, is that this does not, these tables in some kind of form like this do not exist. I could not find. I thought, okay, I'll just go find. Someone must have put together these tables in a way that you could, just copy them, right? They'd just be text somewhere. Nope. I couldn't find them anywhere. I found a book that had the tables, which is what I transcribed. I manually transcribed all of these over from the book. Luckily, there's a lot of repetition here, so it wasn't too bad, but it took a few minutes or so, a couple hours really, to put all this stuff together like this and get it formatted this way. So now you've got all of the table data, or the table data for the graphics rows, the offsets. So this is graphic row 0, 1, 2, 3, and so on and so forth, all the way down. And the low byte and the high byte, and we described how that works before. So you've got that stuff, and you've got and if you were to make a tile engine or a game like this, you've got all your buffers in place. Remember, this has actually got, this map data is a 1K buffer, 4 sectors, 256 byte sectors, so that's built in. You got a disk sector buffer. Actually, this is probably needs to be deleted. I put this in, I was going to use this, and then I decided, well, since we're just temporarily getting the disk sectors, we could use the tile animation check, which is 256 bytes. So it does point to here instead, so you could delete the other one. But because I figured this is only transitory anyway, this is only used every frame, and it's not even used right now. But the idea is to use this every frame to see if we have a tile to animate and to check it off as having been animated. So if you have 5 water tiles and it's tile 0, for instance, this is dummy data. Doesn't matter actually. This data is just garbage. It should all be zeros really, frankly. But anyway, but there's a routine to clear that. So tile 0, if you have 5 tile 0s on your map, they're animated. The first one you find, you change this to a 1. And then when you find the next one, you go here and you say, is it 0? No. Oh, well, we've already animated that one. Skip it. Skip running the animation. And that's how you would that's the concept for how you would basically go through this and quickly determine which tiles need to be animated. Make sure you don't animate them more than once. And then you go draw the screen. Anyway, so that is actually doubling as the sector buffer. You can do that whichever way you want if you want to keep them separate. But I put this in with that intention and then just didn't use it. So there's really extra 256 bytes here that don't need to be here. So anyway, yeah. So you got all these tables now to use and buffer spaces. Again, if you were to build off of this, you've already got a bunch of buffer space added in. I put it at 6,000 because, well, we need something like 6K uninterrupted. So, you know, you can sort out your memory from there. But it's 6,000 hex. So it's right after the graphic tiles going to 4,000, going to screen 2. If you're really ambitious, you could do dual page flipping. You could paint to one screen while you show the other screen, then flip, and then you have really smooth animations if you really want to do that. If you want to take up another 8K memory, and it might be worth it for certain smaller types of programs that may not be a full-blown like RPG. But this method could be used the same way. You just reposition this to 8,000, and then move your tiles to 6,000, and just change the locations in here to refer to that. Move your tiles to 6,000, and then you could do both graphics pages, and you could flip back and forth, and you just have to put the code in to manage that within this program. So stuff like that. This is just ideas. Anyway, thank you. Appreciate everybody watching, and like I said, leave any comments that you might have and questions, and I'll answer them as best I can.